Welcome back to the Deep Dive. Today, we are wrestling with a question that sits right at the intersection of our deepest science and our most profound philosophical beliefs. Do we really need God to explain the universe?
It's a huge one, isn't it?
Yeah.
Arguably the highest stakes debate humanity can have. And we're specifically going to dive deep into the fine-tuning argument for cosmic design.
Right, the idea that our universe is just so precisely calibrated for life that it seems to demand, well, a designer, a super calculating one even.
Exactly. And our sources today, they really span the gamut. We've got rigorous cosmology, particle physics.
And then sharply contrasted with theological apologetics. So our mission here is to take these really high-stakes arguments and figure out, do we have to accept design?
Or are there robust natural alternatives? Things that might make our existence not some miracle, but maybe even inevitable.
Okay, let's set the table then. Define this fine-tuning claim itself. What's the core premise?
Okay, so it's built on the idea that the fundamental parameters, the constants of the universe,
Yeah.
things we measure like the gravitational constant G.
Or the mass of the electron, the strong nuclear force, maybe the vacuum energy density, stuff like that.
Precisely. All those numbers. The argument is that they must be set to what proponents call exacting precision. Just incredibly specific values.
And the consequence is pretty dramatic, right? If any of these were just, nudged slightly.
Yeah, if gravity was infinitesimally stronger, maybe stars collapse too fast. Or if the electron mass was a tiny bit different, you wouldn't get stable molecules.
Then anything interesting, as they say, consciousness, complexity, life as we know it, it just couldn't exist. Poof.
That's the crux. It leads to this choice, framed really well by the astronomer Edward Harrison back in '85. He basically said, you got two options.
Okay, what are they?
Either blind chance that requires multitudes of universes, or design that requires only one.
So the implication is, if these constants were just random dice throws, the odds of hitting our universe, a life-permitting one, are just astronomically low.
Incomprehensibly low, often, compared to finding a universe where life is impossible.
And the visual imagery really drives this home. We've all heard Roger Penrose's famous visualization, haven't we?
Oh, yeah. He talks about the creator pointing to this absurdly tiny volume.
In this massive, multi-dimensional space that represents all possible universes.
Right. Think of every mathematically possible combination of physical constants that's the whole space. Our universe, the one that can support life, it occupies just this minuscule sliver.
A space so small that the probability gets quoted with these wild numbers, like 1 in 10 to the power of 10 to the power of 123.
Exactly. Which seems to scream that its existence is just wildly unlikely without some super-calculating designer who is aiming specifically for that tiny, tiny target.
That sets the philosophical stakes perfectly. Okay, let's move into the arguments from the proponent's side. We've mentioned those terrifyingly small numbers from apologists like William Lane Craig.
Yeah, the claim that intelligent life depends on this complex and delicate balance of initial Big Bang conditions. Life-prohibiting universes being vastly more probable.
But then there's this philosophical dilemma, right? If you have an omnipotent designer, why are the physical laws apparently so constrained? Why this narrow window?
That's the tension. If God is all-powerful, why couldn't God just make a universe that works regardless? Was God, forced to use this specific value for gravity or electromagnetism to get thinking beings?
It sounds like a limit on God's power, which seems to contradict the whole idea of omnipotence.
Well, not necessarily, according to the theological perspective. Thinkers like Francis Collins, for example, suggest the constraint isn't imposed on God, but it's actually a chosen constraint.
Chosen? How so?
God isn't limited by physics, but maybe chooses to work within orderly laws, because the goal is an interesting universe, one with complexity, order, and ultimately maybe one that allows for relationship with creatures who have free will.
Ah, okay. So the constraints, those specific narrow values for the constants, they aren't limits on God's power itself, but they're the means to achieve the goal, complexity, order, maybe relationship.
Exactly. If you choose orderly laws instead of just pure chaos, then those laws, to produce something complex, might necessarily need very specific parameters to work. The order demands the precision.
Okay, see the logic there.
But, and this is a big but, we have to apply some critical thinking here. Even if we accept the staggering improbability for a moment, does that automatically equal design?
Yeah.
This brings us to the purple ball analogy.
Okay, let's hear it. This challenge is relying just on low probability, right?
Right. Imagine a huge bag filled with balls of every conceivable color. You reach in, pull one out, and it's purple.
Okay.
Now, if someone told you the person who filled the bag really loved purple, you might think, aha, confirmation.
Makes sense.
But wait, what if you then tip out all the other balls from the bag and you find they're all different colors? Red, blue, green, yellow, chartreuse, everything but purple.
So billions of non-purple balls.
Exactly. Suddenly, that one purple ball, while still maybe improbable on its own, looks less like specific evidence that the creator only cared about purple.
How does that translate to the universe?
The purple ball is life, or the conditions for it. But the universe has countless other features, the non-purple balls, things like dark energy's specific value, the number of particle generations, the fact that Jupiter has rings.
Features that are just there, part of the universe, but seem totally irrelevant to whether carbon-based life exists or not?
Precisely. So focusing only on the life-permitting aspects, the purple ball might be misleading. It assumes the designer was only interested in that one narrow outcome, ignoring all the other colors in the cosmic bag.
So, the existence of life here, yeah, it's improbable maybe, but it doesn't automatically prove a designer focused just on us, especially if the universe has tons of other features that seem indifferent to life.
This is why the whole debate often gets down to definitions. Theists often make a distinction between proof, which they might concede is impossible for God's existence, and evidence.
Meaning they argue they can present rational evidence for belief based on this observed complexity, even without 100% certainty.
Yeah, it's presented as a rational conviction based on perceived patterns,
Yeah.
not absolute proof.
Okay, but those patterns, the constants themselves, they need to stand up scientifically. Which brings us to the technical refutations. This is where physicists really push back hard on this whole fine-tuning idea, isn't it?
Oh, absolutely. They often argue the whole fine-tuning argument starts with a fundamental error in reasoning.
Which is?
Just calculating an infinitesimally small probability for a specific outcome, like our universe, isn't good enough scientific reasoning.
Yeah.
Low probability events happen all the time.
Right, the lottery winner thing. Someone wins, their specific ticket had crazy low odds, maybe 1 in 300 million, but someone had to win that specific combination. It doesn't mean the lottery was rigged for them.
Exactly. It's the difference between asking, what's the probability of any specific universe existing, versus what's the probability of any life-permitting universe existing. The fine-tuning argument often mixes those up.
Okay, but the refutations get more specific than just that general probability point, right? You mentioned some constants might even be arbitrary, human choices.
Astonishingly, yes.
Yeah.
Many of the poster children for fine-tuning turn out not to be fundamental properties that could be tuned, but parameters effectively chosen by us, by how we define things.
Okay, give us the prime example, the one that's always on the list, the speed of light.
Right. Time.
Right.
Always cited as essential, perfectly tuned. But here's the thing. Since 1983, the speed of light, its numerical value in meters per second, has been fixed by definition.
How?
Because we redefine the meter. It's no longer based on a physical platinum bar in Paris. The meter is now officially defined as the distance light travels in a vacuum in exactly 1 divided by 299,792,458 of a second.
Wait a minute. If the meter is defined using the second and the speed of light, then the speed of light's numerical value can't be fine-tuned. It's locked in by how we set up our units.
Precisely. It's an operational definition. If we decided to use, blargs for distance and ticks for time, the number for $1 would change, but the actual physical speed of light wouldn't. It's about our measurement system.
So focusing on the number 299,792,458 is misleading.
Totally. In theoretical physics, it's super common to use natural units where you just set $200, and boom, the whole mystery of its specific numerical value just evaporates. The fine-tuning argument often relies on keeping those human units like meters and seconds in the picture.
Wow, okay, that really weakens the intuition there. Does the same logic apply to Planck's constant to dollars and the gravitational constant dollars?
It does, largely. Their numerical values also depend heavily on the units we choose, like kilograms, meters, seconds. Saying they are fine-tuned shows a bit of a misunderstanding of how these physics models actually work.
So what does matter in physics then, if not those specific numbers?
What really matters are the dimensionless ratios between these constants. Ratios like the fine structure constant, those are pure numbers, independent of our human unit choices. Those are the potentially fundamental things. Focusing on Vic dollar, G dollar in standard units is kind of mistaking human convention for cosmic decree.
Okay, this is getting really interesting. Let's tackle the big one, the one that feels most compelling intuitively. The expansion rate of the universe.
Ah, yes. This is often the heavyweight argument. Apologists love quoting Stephen Hawking on this.
The quote about how if the expansion rate just 1 second after the Big Bang was off by even 1 part in 10 to the 17th, the universe would have either collapsed back on itself or flown apart too fast for stars.
That's the one. That number, $1017, sounds impossibly precise. It really paints a picture of needing an incredibly fine dial turn at the very beginning.
But the critique is that this quote gets used way out of context. What's the missing piece of physics?
The crucial missing piece is inflationary cosmology. Hawking's original calculation, or the context it came from, often predated or didn't fully incorporate the implications of cosmic inflation.
Okay, remind us what inflation is.
Inflation is the theory that in the very first tiny fraction of a second, like 1035 seconds after the Big Bang, the universe underwent this period of absolutely explosive exponential expansion. It blew up incredibly fast.
By a factor of like $10 or even more, right?
At least. And inflation acts like this giant cosmic steamroller. Imagine the very early universe had wrinkles or curves in its geometry. Inflation stretches everything out so incredibly vast and fast.
That it makes the geometry of space-time almost perfectly flat. Is that the idea?
Exactly. And here's why flatness matters. In cosmology, a perfectly flat universe means its total energy density is precisely equal to something called the critical density. And that critical density is exactly what's needed for the expansion rate to be balanced, not too fast, not too slow.
So inflation doesn't just happen, it forces the universe to have the right density, which in turn fixes the expansion rate.
You got it. Inflation automatically drives the expansion rate very close to that critical rate. It's a physical mechanism. So the probability isn't 1 in 1017. Given inflation, the probability of getting the right expansion rate is basically 100%.
But it's not fine-tuned. It's a natural consequence of physics in the early universe.
Pretty much. Assuming inflation happened, which is a core part of the standard cosmological model now, supported by lots of evidence like the cosmic microwave background patterns.
Okay, that definitely takes the wind out of the sails of the expansion rate argument. Let's look at force strengths. Specifically, that huge ratio between gravity and electromagnetism. It's like $10 or something.
Yeah, gravity is incredibly weak compared to electromagnetism. That number is often cited. The argument is, if gravity were a bit stronger, maybe atoms couldn't hold themselves up against it. If it were weaker, stars and galaxies wouldn't form.
Seems like another knife-edge balance.
It seems like it. But again, that 10 ratio is a bit deceptive. Why? Because we're comparing the forces acting between really, really tiny masses, like a proton and an electron.
Ah, so the ratio depends on the masses involved.
Exactly. The strength of gravity isn't some universal number. It depends on what masses you're talking about. That ratio looks so huge primarily because the masses of elementary particles are incredibly tiny compared to the natural mass scale in physics, which is the Planck mass.
The Planck mass, defined by city ball G in all dollars.
Right. If elementary particles had masses closer to the Planck mass, gravity would actually be stronger than the electric force between them. So the real mystery isn't so much the ratio itself, but why are particle masses so small compared to the Planck scale? That smallness is what generates the huge ratio we see.
That flips the question completely. Okay, sticking with particles, what about the claim, often from someone like Hugh Ross, that the ratio of protons to electrons, Na and PLI, has to be exactly 1? If it were off even slightly, electrical repulsion would just blow everything apart, overwhelming gravity.
Right, that's another common one. But the ratio is exactly 1. Why? Because the universe has to be electrically neutral overall.
It's not a coincidence.
Not at all. It's a direct consequence of a fundamental law, charge conservation. The total electric charge must be conserved. If you started with a net charge imbalance, say, way more protons than electrons, the resulting electromagnetic forces would be so overwhelmingly dominant that structures like galaxies, stars, even atoms probably couldn't form. So electrical neutrality isn't fine-tuning. It's a prerequisite for any kind of complex structure formation baked in by a fundamental conservation law.
Okay, that makes sense. Now, we absolutely cannot talk about fine-tuning without discussing Fred Hoyle and the carbon resonance. This is often presented as the one big success story for anthropic reasoning, right?
It's the classic example, yeah. Back in the 50s, Hoyle was figuring out how stars make heavier elements. He realized that for stars to produce enough carbon, which is obviously essential for life as we know it, there needed to be a special energy level, a resonance in the carbon-12 nucleus at a very specific energy, around 7.7 MeGa.
And why was that needed?
It acts like a doorway or a funnel. It makes the fusion of 3 helium nuclei into 1 carbon nucleus happen much, much more efficiently. Without this specific energy level, stars wouldn't produce much carbon at all. They'd mostly make oxygen.
And he predicted this energy level before it was experimentally found, based on the need for carbon for life.
He did. He basically said, for us to be here, this state must exist, and pressured physicists to look for it, and they found it right where he predicted. It looks like a slam dunk for anthropic fine-tuning.
So case closed on that one. Design confirmed.
Well, hold on. It sounds incredible, and it was a brilliant prediction. But later, more rigorous calculations by nuclear physicists looking at it in detail, they kind of tempered that conclusion. Yes, the resonance state exists, and it's important. But it turns out it's not quite as exquisitely fine-tuned as initially thought. The calculations showed that you'd still get adequate carbon production for life, even if that resonance energy level was anywhere from just above the energy of the helium nuclei up to about 7.933 MeV.
That sounds like a bigger range than a knife edge.
It is. It's a range of about 300 keDUS, which is actually pretty broad in nuclear physics terms. It's a range that standard nuclear theory wouldn't find particularly surprising. So yes, resonance needs to be in the right ballpark, but it's not tuned to an absurd precision. Hoyle's prediction was great, but the constant itself seems fairly robust, not brittle.
Okay, so summarizing this whole technical section, the fine-tuning argument sounds powerful, especially with those big numbers, but when you look closely,
It often relies on misinterpreting probabilities, or focusing on dimensional constants whose values depend on our human unit choices, or it ignores major physics developments like inflation that actually explain the supposed fine-tunings naturally.
and even the best case, the carbon resonance, turns out to be less fine-tuned than claimed.
That seems to be the consensus from physicists who dig into the details. The case for design, based on these specific constants, seems to really weaken under scrutiny, which naturally moves the conversation away from these static parameters.
And towards the origin of the universe itself, the very beginning.
Exactly. Which brings us to another major pillar of the design argument, the Kalam cosmological argument, or KCA.
Right, the KCA. It's that deductive argument trying to prove a creator based on the idea that the universe had a beginning.
That's it. Stated very simply. Premise 1, everything that begins to exist has a cause. Premise 2, the universe began to exist. Conclusion, therefore the universe has a cause.
And that cause is argued to be a necessary uncaused creator, i.e. God. For the conclusion to hold, both premises have to be solid.
Absolutely. If either premise falls, the deductive argument fails. Let's tackle premise 1 first. Everything that begins to exist has a cause. Why do many modern physicists say, well, hang on?
Because of quantum mechanics.
Precisely. It seems to fail empirically at the quantum level. We observe stuff happening all the time. Radioactive decay of an atom, an electron jumping energy levels, virtual particles popping in and out of existence in the vacuum.
And these things are spontaneous, unpredictable.
Yes, and crucially, they seem to occur without a direct cause in the classical sense we usually think of. We can calculate the probability that a specific uranium atom will decay in the next hour, but we cannot predict when it will decay or what causes that specific decay event at that moment. It just happens, probabilistically.
So the idea of universal causality, that everything needs a prior cause, seems to break down at the most fundamental level we can probe.
It certainly appears that way based on our best understanding of quantum physics.
Mm-hmm.
And this has a really interesting theological knock-on effect too, doesn't it?
How so?
Well, if the very fabric of reality operates on this inherent randomness, this quantum indeterminacy, how does that fit with the idea of a meticulous designer who has specific purposes in mind for every single detail, a God who planned everything out precisely?
Right. A God relying on uncaused, spontaneous quantum events seems different from the classical image of a grand architect meticulously placing every brick.
It introduces a level of randomness, or perhaps freedom, into the system that seems to clash with some traditional notions of deterministic design. It makes the classical KCA premise problematic, even from a theological angle sometimes.
Okay, let's look at premise 2 then. The universe began to exist. This was traditionally linked to the idea of the Big Bang starting from an infinitely dense point, a singularity.
Yes, and for decades, apologists really leaned on the 1970 Hawking-Penrose singularity theorems. These mathematical theorems seem to prove that, under general relativity, if you trace the universe back in time, you inevitably hit this point of infinite density, infinite temperature, infinite curvature.
The singularity, which was then interpreted as the absolute beginning of space and time itself, the moment of creation.
Exactly. It seemed like science had proven the universe had a definite start,
Mm.
fulfilling premise 2 perfectly.
Yeah.
But, and again, there's a but.
What was the limitation of those 1970 theorems?
Their biggest limitation was that they relied only on Einstein's general relativity. And we know general relativity is fantastic for describing gravity on large scales, planets, stars, galaxies, but it breaks down completely at the extreme conditions found at the center of black holes and, crucially, at the very beginning of the universe.
Because it doesn't include quantum mechanics.
Bingo. You need a theory of quantum gravity to describe that initial state, and we don't have a complete one yet. But we know enough about quantum effects to understand what happens as you approach that supposed singularity.
What does happen?
As you get down to the Planck scale, the Planck time, 1043 seconds, and Planck length, 1035 meters, quantum fluctuations of space-time itself become dominant. The smooth geometry described by general relativity dissolves into a quantum foam. And in that realm, the concept of a single, infinitely dense point, the singularity just doesn't hold up.
So Hawking himself later revised this.
He did. He stated quite clearly that once you consider quantum effects, there was in fact no singularity. The universe likely began with a finite, although incredibly small, size and finite density. It wasn't an infinitesimal point emerging from absolute nothingness. It was likely a transition within the laws of physics from a quantum state.
So premise 2, interpreted as the universe began from a singularity, is likely false based on physics beyond general relativity.
It appears so. The universe had a beginning in the sense of our current expansion phase starting, but likely not from the classical singularity that the KCA often relied upon.
And does this also deal with that argument you sometimes hear that an eternal universe is impossible because it would take infinite time to reach today?
Yes. That argument is based on a misunderstanding of infinity. An eternally existing universe, one with no beginning, doesn't mean it started in an infinite time ago. It means it never started. You can count backwards forever without hitting zero. The time interval isn't infinite, it's just unbounded in the past. It's mathematically and physically perfectly coherent. Assuming everything must have a start time is a philosophical assumption, not a logical or physical necessity.
Okay, so if the fine-tuning of constants seems explainable by natural physics, and the beginning wasn't necessarily a singularity demanding an external cause, but likely a quantum event.
Then the door swings wide open for exploring natural, non-created origins for the universe. And this leads us straight into the major scientific alternatives to a designer.
The biggest one being the multiverse, right?
Yeah.
Especially when viewed through the weak entropic principle, WP.
Exactly. The multiverse is probably the most discussed alternative. First, let's just nail down the WP.
Okay, what is the weak anthropic principle?
It's actually quite simple, almost a tautology. It just says, the conditions and constants we observe in our universe must be compatible with the existence of observers, like us. Because if they weren't, well, we wouldn't be here to observe them.
It's an observation selection effect. Like, you can't observe a universe that's lethal to you.
Precisely. Now, combine that simple principle with the idea of a multiverse, a vast, perhaps infinite ensemble of other universes, potentially generated naturally through processes like eternal inflation.
Where each bubble universe in this multiverse might have different physical constants, different laws, maybe even different dimensions, all determined randomly.
That's the picture many models suggest.
Yeah.
If you have this huge cosmic landscape of universes, each with randomly varying parameters, then the fine-tuning problem just dissolves.
Because it's no longer surprising that we find ourselves in a universe with life-friendly parameters. Out of all the universes out there, we could only exist in one like this.
Exactly. We didn't win a lottery against impossible odds because the game was rigged. We just find ourselves living in the universe that happened to draw the winning numbers for life, because all the other universes with losing numbers simply don't have observers like us asking the question.
So the statement flips. Our universe is not fine-tuned for life.
Rather, life is fine-tuned to our universe. Life arose here because the conditions happen to be suitable. In another universe with different constants, maybe different forms of complexity or no life at all would exist.
And is the multiverse just a philosophical idea, or is there actual physics pointing towards it?
It's increasingly suggested by our fundamental theories. String theory landscapes, eternal inflation models. These frameworks, which are serious attempts to understand fundamental physics, often naturally predict the existence of multiple universes. It's not just pulled out of thin air to solve fine-tuning. It seems to be a consequence of where the physics is leading.
So the multiverse plus the WA provides a compelling natural explanation for why our constants look fine-tuned.
It does. But there's more. Physics also offers explanations for the origin itself, without needing a creator, using quantum mechanics again.
You mean quantum tunneling?
Exactly. Quantum tunneling. It sounds like sci-fi, but it's a 100% real, experimentally verified quantum effect.
Explain it simply.
Okay, imagine a ball rolling towards a hill. Classically, if the ball doesn't have enough energy to roll over the top of the hill, it just rolls back down.
Right.
But in the quantum world, because particles also behave like waves and have uncertain positions, there's a small but non-zero probability that the particle can just appear on the other side of the hill, even without enough energy to go over it. It tunnels through the energy barrier.
And this actually happens.
Absolutely. It's crucial for how the sun generates energy through fusion. It's used in devices like the scanning tunneling microscope, which lets us image individual atoms. It's real, confirmed physics.
Okay, so how do cosmologists use this tiny effect to explain the whole universe?
They modeled the very beginning. The universe itself, the whole space-time manifold, can be thought of as originating via a quantum tunneling event. Tunneling from, well, from nothing.
Now, when physicists say nothing, they don't mean philosophical nothingness, right?
Usually not, no. They typically mean a state before our classical space-time existed. Maybe a quantum vacuum state, a sea of quantum fluctuations. Perhaps a state described by quantum gravity, basically. A pre-geometric, pre-time state governed by quantum rules, but not the empty void of philosophy.
So the universe effectively tunneled into existence spontaneously from this prior quantum state, like a particle tunneling through a barrier.
That's the model. It provides a complete, self-contained scenario for the natural origin of the universe, consistent with known physics that does not require an external trigger or creator. The creation event itself could be a natural quantum process.
Wow. Okay, that's a profoundly different picture. A universe capable of beginning itself through quantum laws. And this ties into one last big mystery, the arrow of time and entropy.
Yes, the puzzle of why the early universe started in such a highly ordered, low-entropy state. The second law of thermodynamics says entropy, disorder, always increases. So why wasn't the universe born as a high-entropy mess?
Which is necessary for complexity in life to develop later.
Absolutely. The Hartle-Hawking no-boundary proposal offers a potential explanation using symmetry, the idea of a biverse.
A biverse, like two universes.
Sort of. The model suggests our universe, expanding forward in our direction of time, might be paired with a mirror image universe expanding backward in time, away from the initial state.
With an opposing arrow of time, how is the arrow of time defined here?
It's defined by the direction of increasing entropy. So you have this initial state, maybe the Big Bang moment or the quantum tunneling event.
Let's call it $2.
Okay, $2. Entropy increases as you move away from $2 in the positive time direction, our universe. And in this model, entropy also increases as you move away from $2 in the negative time direction, the mirror universe.
Ah, so T alpha isn't a true beginning, but more like a midpoint of minimum entropy, the point of maximum order.
Exactly. It naturally explains why entropy was low near the start of our expansion. It had to be, if entropy increases in both time directions away from that central state. It's a consequence of the symmetry of the model and the thermodynamic definition of time's arrow.
That's elegant. It uses fundamental physics principles, quantum mechanics, symmetry to potentially explain both the origin and the initial low entropy state.
It provides immense explanatory power, yeah. So we've gone from this picture of incredible, seemingly miraculous fine-tuning requiring a designer, to a picture where physical mechanisms like inflation, the multiverse, quantum tunneling, and symmetry principles might make our universe's properties seem much more, well, natural, even inevitable.
Okay, let's bring this back to philosophy then. How should all this scientific counter-evidence change how we think about the original design argument?
Well, one powerful critique comes from applying Bayesian probability theory, specifically work by people like Jeffries and Ikeda. They looked at the core probabilistic claim of the design argument.
Which is basically, naturalism makes a life-friendly universe very improbable, therefore observing a life-friendly universe makes naturalism itself improbable.
Right, but Jeffries and Ikeda argue this commits a statistical error, often called the prosecutor's fallacy.
Okay, break that down. PEH is not PHE.
Exactly. The probability of the evidence, E, a life-friendly universe, Given the hypothesis, H, naturalism, might be low. But that's not the same as the probability of the hypothesis naturalism being true, given the evidence that we live in a life-friendly universe.
Give us that disease analogy again.
Okay. Rare disease, 1 in 10,000 people have it. Test is 99% accurate, catches 99% of sick people, and gives false positive to 1% of healthy people. You test positive, what's the chance you actually have the disease?
Intuition says 99%.
Right. But using Bayes' theorem, because the disease is so rare, most positive results will actually be false positives from the much larger group of healthy people. The actual probability you have the disease, given the positive test, is closer to 1%.
Wow. Okay. So how does that apply to the universe?
Even if the probability of our specific universe arising under naturalism, the key in naturalism, seems incredibly low, you have to consider the vast number of possible universes that naturalism, especially via multiverse theories, might allow for. When you crunch the Bayesian numbers properly, Jeffries and Okita found something counterintuitive.
What do they find?
They found that learning the universe is life-friendly actually ends up supporting naturalism slightly more than design, or at least doesn't favor design.
Why?
Because while life might be rare in any given naturalistic universe, the sheer number of potential naturalistic universes is so vast that finding some life-friendly ones isn't that surprising within that framework. The argument, they conclude, is basically useless for proving a designer statistically.
Okay, that's a heavy philosophical point. It all seems to push towards a certain stance, doesn't it? Kind of intellectual humility.
Absolutely. I think it's vital, regardless of your ultimate beliefs, to acknowledge that things like the precise values of constants, the origin of life, and for that matter, the existence of suffering and evil, these are still, in many ways, great mysteries.
And we should be wary of anyone claiming absolute certainty on these huge questions.
Exactly. Excessive confidence, whether from theists or atheists, about knowing the definitive answers to these profound cosmic questions should probably be treated with a healthy dose of suspicion.
This leads to that idea of a symmetry of skepticism, right?
I think that's a fair way to put it. If a theist reasonably says, look, I don't fully understand why they're suffering, but I trust there's a deeper reason consistent with a good God, then the agnostic or skeptic should equally be allowed to say, look, we don't have the final theory of everything yet to explain all the constants, but I trust that a natural scientific explanation will eventually be found.
It balances faith in a divine explanation against faith in the progress of scientific explanation.
Yes, both require a degree of trust in something currently unknown.
But ultimately, the question itself, does the universe need a creator? It still feels immensely important.
Oh, undoubtedly. As someone framed it, this question is either the most important truth in the world or inconsequential. The sheer possibility that it could be the most important truth makes exploring it, digging into the arguments like we've done today, incredibly worthwhile.
Even if the scientific arguments against fine-tuning seem strong.
Yes. And what we learn from the physics itself is fascinating, regardless of the philosophical outcome. The universe seems far more self-sufficient, more governed by deep internal symmetries, and perhaps less fragile or delicately balanced than the simplest version of the fine-tuning argument suggests.
Okay, this has been an incredibly detailed deep dive. Let's try to synthesize. We've seen that the fine-tuning argument, while it feels powerful and intuitive,
Often rests on shaky ground when you examine the science closely. It can misuse probability, rely on constants tied to human units, or ignore physics like inflation that provides natural explanations.
we've explored how rigorous physics points towards mechanisms like inflation, quantum tunneling, symmetry principles, perhaps the multiverse, all suggesting that our universe's characteristics might be, if not inevitable, at least far less improbable than claimed.
And many parameters claimed to be fine-tuned are actually fixed, either by fundamental conservation laws, like charge neutrality, or even by how we define our units, like the speed of light.
All right, so let's leave our listeners with a final provocative thought to chew on. It relates to those fundamental laws themselves.
Okay, so the scientific perspective increasingly sees the great conservation laws, conservation of energy, momentum, angular momentum, not as arbitrary rules built into the universe or handed down by decree.
But as consequences of something deeper.
Yes, as consequences of symmetry. Specifically, the requirement that the laws of physics must be the same regardless of your location, leading to momentum conservation, your orientation, leading to angular momentum conservation, or the time you measure them, leading to energy conservation. It's called Noether's theorem.
So these fundamental laws arise from the simple, powerful idea that physics must be consistent from all points of view invariance.
That's the core idea. The laws emerge from the very structure of space-time and the demand for objective consistency.
So here's the thought for you, the listener. If our most fundamental physical laws aren't arbitrary decrees, but instead emerged necessarily from these deep symmetry principles, what does that imply about the nature of constraints on any potential creator?
Were these laws, in some sense, inevitable from the start? Did a creator even have a choice about them? If they emerge from the very logic of consistent reality, does symmetry itself constrain creation?
That's definitely something to mull over. Were the laws of physics baked in from the absolute beginning, leaving no room for tinkering? Something for you to explore.
Indeed. Well, thank you for joining us on this deep dive into the cosmos, fine-tuning, and the question of design.
It's been fascinating. We'll catch you on the next deep dive.